Feedback. So there will be an online feedback which will be uploaded either today or tomorrow. So when you go back, make sure that you upload your feedback. You get your TA only after you do that.
The instructors also give some feedback.
You can. We'll later make an announcement about
the feedback, but if the lecturers did give a feedback, because ICTS often in the annual report put quotes like, R Saulson said this.
So specifically we'll write to the next.
Sure.
Okay.
Oh, absolutely.
Yeah, that would be very useful for
That's right. I can speak for all three of us.
Yeah.
Happy to do that. Okay. Nice to see you all again. And now is the time in the week when I get to talk about a kind of noise that makes me smile. If you see me smiling, it's because I find thermal noise very charming, even though I should be mad at it because it's a kind of noise that we have to fight. But as a physicist, I find it beautiful in part because it's got this fundamental constant that is always floating around, Boltzmann's constant. It's really interesting physics here. And even, I find myself surprised to say this, but I will, it has also interesting and potentially beautiful material science in it. So I hope I can convey some of the charm of this aspect of our business here. Okay. So I'll start with a historical review of the first encounter of physicists to thermal noise, and that's the story of Brownian motion, which was at one time a major crisis in physics, and then when the breakthrough occurred, it was a major breakthrough in physics and in chemistry, as it turned out. It presaged a much deeper understanding of physics that evolved through the course of the 20th century. And after I've reviewed the basic physics, I will talk about how thermal noise comes into interferometers, and then talk about the issues that surround what is the overall level of thermal noise and what sorts of things we can do to make it as small as we know how to make it. You've seen me show this slide before. The numbers aren't quite so ridiculously scary for the overall amplitude as they are for seismic noise. On the other hand, for seismic noise, we can and we do build filters that can keep the noise outside the instrument, at least in a large range of frequencies, whereas the thermal noise of the Brownian motion is generated right at the most sensitive parts of the instrument. So filtering in any conventional sense, there's no way to do it. So here's the history. I'm going to show you a number of sketches, and I want you to ponder the tedium that went into recording these sketches. This is the record of the position as seen through a microscope of a little bit of dust that wasn't quite so little because you could see it in a microscope over the course of, I don't know, a number of minutes. And this is the phenomenon called Brownian motion that was first described in 1827 by Robert Brown, who gave his name to the phenomenon. And when he reported it, it was a tremendous puzzle. And Brown, by the way, had a job description that we don't have anymore. He was a microscopist. That was his brand of physics or science, learning to what you could learn by looking through a microscope. And you'll recall that really the first major discovery of the application of the microscope as a scientific tool was the discovery of living cells. And that played out for a long time, okay? This is much later than Leeuwenhoek's invention of the microscope. So probably many people before Brown had seen Brownian motion without knowing that they should ponder it and think it interesting. But the issue that Brown brought forward was, here's stuff, little bits of inert matter that as far as we know aren't alive, and yet under the microscope they look more or less like they have the same activity as living things. And so Brown, if you read what he was worried about, he actually was kind of not sure he shouldn't backpedal on the distinction between inert matter and living matter. It was that confusing what could be the cause of Brownian motion. And the part of his story that actually really amuses me is he thought he could do a crucial experiment, and that is to get some dust where someone had ground up a little chunk of the Great Sphinx in Egypt. He really wanted to see whether that exhibited Brownian motion as well, and I think he thought it would be a test case for, is dead matter, is rock alive or not? So clearly the guy was really good to have noticed this where hundreds of people had noticed it before, but clearly he was not quite in the modern era of thinking about things. Anyway, he bequeathed to physics an observation of something that remained a puzzle for close to 8 decades. It was only resolved, let's see, did I lose a slide? No, okay. I'll jump ahead and tell you something that doesn't appear until a later slide here. It was only resolved in 1905 by Einstein, and it's one of his 3 great papers from the so-called miracle year of 1905. And it's one of the things that was mentioned in his Nobel Prize citation. So this was a big deal, and I'll convince you what a big deal it is. So here is what finally became the explanation of Brownian motion. It is, in fact, that water is made of molecules. Those molecules randomly collide with the microscopically visible Brownian particle. And that set of random collisions from all sides yields a random walk, like I showed you in that diagram a few slides ago. Here's another diagram. Physics researchers did this, okay? Sat and say, okay, the particle's here, now it's here, wait another few seconds, it's here. Well, it's hard for me to think of something else that could have been as tedious as that. And part of the fun that I'm making of it, or the tedium that I think was involved, is all of these things were being recorded as if maybe a pattern would be found. And in fact, I will show you how a pattern was extracted from it. But boy, this is about as random a thing as there is. So even knowing how to step back from the observation of the history of this particle, observation of the history of this particle, observation of the history of this particle, and know how to ask the question, what pattern is hidden in there, or what clues are there that will tell us how to understand this Brownian motion. It took some insight, and this insight gradually accumulated over those 8 decades between 1827 and 1905. And maybe I'll skip ahead in the history a little bit. There was a second Nobel Prize awarded for study of Brownian motion in 1926 to Jean Perrin. This was such a big deal when it was explained that that the follow-up studies to Einstein's explanation got a second Nobel Prize. I'm sorry, you see a pattern? Okay. Yeah, all right, you're as bad as Brown, I think. There you go. Okay, so is there a pattern to all these random walks? All the diagrams I've been showing you so far have been the tracks of individual particles recorded at intervals over a long period of time. This is a different kind of diagram. It represents the center of these concentric circles, represents the starting point of each of a bunch of many particles, and then the dot represents the the position that the particle had reached at the end of a chosen measurement interval for one particle, another, a third, a fourth, and so on. Okay, so here are those endpoints. They're scattered, but it looks like there is, well, they're more dense near the center, as if it's hard to get far away when you drift under Brownian motion. So eventually people focused on this measure of saying, what is the mean of the square of the distance that a particle moves over a particular finite measuring interval? Here's yet another version of one of these graphs where we've got displacement just done as a single variable here, that as a function of time, and there's some individual tracks. And the fact that could be extracted from this, averaging over many Brownian particle tracks, is that the mean square displacement grows as a single power of time. And if you work harder, you can do experiments that maybe can show a temperature dependence. I'm not actually 100% sure that I know why I wrote that here. But you can also show that the amount of drift does depend on the size of the particle and on the viscosity of the liquid. So here was Einstein's great statement. He said, on the basis of theoretical insight, that the mean square displacement of a particle over an interval t is equal to t times twice Boltzmann's constant times the temperature times a coefficient called the mobility, which is related to the drag on the particle. And the theoretical idea that went into this was that, in fact, the water is made up of individual molecules. And it's hard for us today to get into the frame of mind where that would be controversial. But in fact, the way this discovery was received at the time was, in fact, that this was the first clear physical demonstration that the molecular theory of matter was, in fact, correct. When we learn sort of our baby version of chemical history, we learn about Dalton and all these other folks who spotted lots of regularities in chemistry that could be explained, that made the most sense in terms of a molecular picture, and we look back and say, yeah, they proved that matter was made of molecules. But there was also a very influential school of thinking that said there's no possible observational way to verify the existence of things so small so that our physical theories shouldn't make reference to unobservable phenomena, and we should just declare as a matter of scientific principle that we will never know whether the molecular theory is correct or not. And this exploded that. Okay? It made molecules real. And sort of the currency of that proof was being able to say exactly how massive a molecule was. To say, a mole of stuff has 6.02 times 10 to the 23rd molecules in it. Okay? Once you could do that, they were not hypothetical. You knew exactly the sizes of things. So, establish the existence of molecules, establish the molecular theory of heat. Heat is the microscopic motion of molecules. And also, as we'll see in a moment, this also leads pretty directly to an understanding of friction, of dissipation phenomena, as something related to random motions of microscopic degrees of freedom. That is the individual molecules that make up the macroscopic stuff. that the universe is made of. Okay, here's where I remembered in my slides to mention Perrin's Nobel Prize for following up the Einstein theory with the most detailed observations made. And you can still buy, there's a book still in print by Perrin called Atoms, where he describes all of his measurements. And not long after that Nobel Prize, another big thing came out. Johnson said, oh, look, there's an electrical analog, and we still call it Johnson noise. That started to make things even more interesting, that an ostensibly rather different phenomenon, namely noise of a current, should really have some kind of unified description with the motion of dust particles in a liquid. Now, there have been many revisitings of the best way to describe the kind of phenomenon that we call Brownian motion, and there continue to be those. What I think is the clearest and most easy to use version of a general statement of the connection of what Brownian phenomena are out there in the world comes in the set of papers. There's 2 or 3 papers by Callan and a variety of co-authors in the early 1950s that give a generalized version of Einstein's relation called the fluctuation-dissipation theorem. And perhaps I like it because it gives the statement in the frequency domain, and I've gotten really into thinking about the world in the frequency domain. So let me walk you through the statement of this theorem, because although it looks slightly daunting perhaps, it actually repays study and gives you a lot of insight. So on the left-hand side, the measure of the strength of the Brownian motion-like phenomenon is the power spectrum of whatever it is. Power spectrum of a displacement of a mechanical thing, power spectrum of a voltage in a circuit, or as Callan showed in some of those papers, there's a huge number of different phenomena that you could plug in for that variable. We, in fact, will be mostly, in our business, interested in displacements. So I've marked it with an X. So here's the power spectrum of the thermal noise displacement on the left-hand side. And on the right-hand side, here is a coefficient that involves K Boltzmann and the absolute temperature, an explicit frequency factor, f squared in the denominator. But then the source term over here is something I want us to dwell on a little bit. It's the real part of the admittance of the system, which is a complex frequency-dependent quantity I will define in just a second. If we're talking about a mechanical system in particular, the admittance is the complex frequency-dependent ratio of the velocity at the point you are considering, whose displacement you care about, divided by the applied force. In other words, this is a kind of a frequency response. And let me skip ahead one slide to a diagram. Okay, so let's say I have some system. You may recognize it, a mass hung as a pendulum from a rigid support. And let's say that in this case, I want to know what's going to be the thermal noise, the Brownian motion equivalent of the center of mass of this object. I'm invited by Callan to measure the admittance, and I measure it by applying a sinusoidal force, first at one frequency, then at another, to build up a complete description of what I want as a function of all frequencies that I care about. So apply a sinusoidal force and measure the sinusoidal response, and in particular measure the velocity of that response. And build that up for all frequencies I care about, and record in particular the complex ratio, because there's an amplitude to this ratio. How big is the sinusoidal velocity for a given amplitude of force, and also a phase shift between the velocity response and the force. So I've got myself a complex frequency response describing my system. And now Callan says, for the purposes of estimating the noise, I want the real part of that. Put the imaginary part to the side. The real part of that, and plug that in, multiply by this coefficient, and the strength of that real part determines the strength of the fluctuating noise. Now, let's pause a little bit more to see why it's the real part and what that is telling us. If I've got a pure spring here, and I apply a force at frequencies below the resonant frequency, the displacement is in phase with the force. So the velocity is in quadrature with the force. So that says that the real part of the velocity response below resonance for a pure mass spring system is 0. Above the resonance, the displacement response is in pure antiphase. The velocity response is in quadrature phase. So again, the real part is 0 for the pure mass spring system. Okay? The only way to get a non-zero real part for the admittance is to have dissipation. Is to add in a dash pot or some moral equivalent, something else that does something besides inertia and besides elasticity. So the real part is the particular clever version of the particular clever measure of dissipation that turns out to be what you want to be the source for generalized Brownian motion. And that's why this is called the fluctuation-dissipation theorem, because on the right-hand side we have a measure of the dissipation in our system, and on the left-hand side the strength of the fluctuation. Okay.
It's the 1 over f squared because you have a fluctuating force and you're thinking of displacement?
Yeah, it's something as boring as that. Yes. But I didn't mean to say your suggestion is boring, but it's not the most exciting thing because there's a simple explanation. Whereas that it should be the admittance as opposed to something else you have to work and think about, and then the deep physics is that it's got a k Boltzmann T and that it is some measure of dissipation that tells you what this is. So you stare at that and you say, well, let's say I don't like Brownian motion. I don't want my mirror to move a lot for this reason. What can I do? And there are two things that would jump out at you. Maybe you can reduce the dissipation. Maybe you should lower the temperature. Those are the two strategies that suggest themselves. And let's explore what's involved there. Okay, so that's our diagram displaying what admittance is. All right. Now, I want to lead us through an apparent contradiction, or at least a seemingly puzzling thing, as a path to gaining some insight. So, let's compare this statement that we're invited to reduce the dissipation as a way of reducing the amplitude of generalized Brownian motion of thermal noise to the part, the thing closest to this that most of us learn in our first course in thermodynamics, namely the equipartition theorem. And the equipartition theorem can be stated this way, that each degree of freedom of a system has on average an energy of 1/2 k Boltzmann T associated with thermal fluctuations. And I've got a particular example here. I'll pick out for a harmonic oscillator the degree of freedom associated with its displacement of the stretching of the spring. 1/2 kx squared equals 1/2 k Boltzmann T. And you can just plug in the parameters of your favorite harmonic oscillator, 10 kilogram mass in a 1 Hertz pendulum, has the amount of energy associated with a RMS displacement, of 3 times 10 to the minus 12 meters. Now, that's fine, okay? I'm not about to say there's anything wrong with what I just wrote there. But does this invite you to reduce that amplitude by reducing the amount of dissipation? Does the concept of dissipation appear anywhere on this slide explicitly? No. So what's wrong with our insight from Callan's fluctuation dissipation theorem, which says, oh, I've got a measure of dissipation over here. If I make that smaller, the fluctuations will be smaller. How can that be consistent with this that says it's only the temperature that matters, nothing else? All right. They aren't in contradiction, but finding out how those different statements can both be true is worth doing. And is this visible from the middle? Or those? Do you see that trace? And do you see that trace? Okay. Is that a no or yes? Yes. Good. Okay. All right. Now let me tell you what it is that you're seeing. This is a graph made on old-fashioned chart recorder paper. This is a paper from the late 50s, I think. And the x-axis in all these graphs is the time, and the y-axis is the angular displacement as a function of time of a small torsion pendulum. And torsion balances used to be, the precise lab instrument for measuring small currents, right? Every lab used to have them, and the limits to performance of torsion balances used to be, a classic problem everyone had to know about to know why they couldn't make better electrical measurements. So this was actually a practically interesting result when it was announced. So one nice thing about a torsion balance, the way these things were constructed, okay, it was an electrical measuring instrument, so in addition to the inertia element and the fine wire whose twisting was the restoring element, so it's kind of a mass on a spring, except it's all about angular motion and 1 degree of freedom, is that the whole thing was there because you wanted to apply a current to a coil attached to that inertia element and measure a torque by the interaction between that current in the coil and a magnet that was near the coil. So one thing you could do very easily was put the coil, you connect in series with the coil a resistor to change the resistance in that circuit, and that changed the amount of damping. You could go from a high Q to a low Q oscillator by your choice of that resistor. And what we see here is just the fluctuations of the angle of a single torsion balance instrument, the very same one in all 3 cases, except with a different resistor hooked up with the coil so that there was different damping. And so the question is, what is the same about those 3 time traces of theta versus t, and what's different about those 3 time traces of theta versus t? Who'd like to propose either a similarity or a difference? So, say it louder, Ernie. Which is the same? The RMS, yes, absolutely. They have the same RMS excursion. They both sort of barely fit in that scale, that was the full scale of the chart recording, and they spend more time at low displacement than at high, but explore that, yeah. So the RMS is the same. Okay, what's the distinction between them? Could you tell them apart? If I cut this into 3 pieces, could you sort them and match them? Okay. by which you mean it looks the closest to a sinusoid. Good, okay. Which looks the least like a sinusoid? The top, and this one kind of in between. Okay, now, the statement, let's remind ourselves of the statement of the equipartition theorem. The equipartition theorem is all about RMS. It says that the RMS depends only on the temperature. And here, these three different cases, something was changed, but the temperature wasn't. It was just room temperature, 300 K. And indeed, the RMS displacement of this physical system is the same. The equipartition theorem says nothing about the spectral character of the displacements that, summed up all together, give the RMS displacement. So the place to look for the lack of contradiction between the equipartition theorem and the fluctuation dissipation theorem is to realize precisely that the equipartition theorem tells you about the spectral character, not just about the overall level. Of course, if you do an integral of that power spectrum over all frequencies, there's a theorem that states the integral of the power spectrum over all frequencies is the mean square. So, equipartition theorem tells us that the integral of this power spectrum has to be governed by the equipartition theorem, but that by changing the dissipation, we can change the spectral character. So here is an example. I didn't actually compute this from that data, but just to illustrate the point, here is a noise spectrum appropriate to three different oscillators of the same resonant frequency, each driven by thermal noise, each having their noise power spectrum governed by the fluctuation dissipation theorem, but with different amounts of dissipation. Here's a low Q, a medium Q, and a high Q system. And it's a little bit hard to see because I chose to plot it on a log-log scale, and when you do integrals, that's sort of the last thing to be able to, last thing you should do to be able to see that the integrals over all frequencies are the same, but they are. We've got a broad peak that's low here, a narrower intermediate height peak, and still narrower higher peak. They have the same integral. But now, what else can we say about the relationship between the low Q system and the high Q system? When we make the high Q system, the one with the sharp peak, by reducing dissipation, what happens to the spectral strength of this thermal noise displacement? The peak is higher. How about well below the peak? Comes down. What about well above the peak? Comes down. Okay, so here is where we can see what that fluctuation dissipation theorem is saying. It's saying any place where the dynamics isn't really interesting, the naive thing that we first thought we saw in the fluctuation dissipation theorem is true. Namely, lower the dissipation level and the noise goes down. But the role of that being the admittance as the measure of dissipation is that the admittance contains the fact that there's a resonance. And it's the admittance itself that has its resonant denominator says, whoops, when I reduce the dissipation, a little bit of force makes me swing a lot, and it all hangs together and guarantees that it's consistent with the equipartition theorem. So there's a tremendous amount of cleverness in nature embodied in the statement of the fluctuation dissipation theorem. Okay, so let me, before I move on to this slide, let me draw the lesson that we're going to draw for the application in gravity wave detectors. The lesson is we can't change the RMS motion of the thermal displacements of the various degrees of freedom in our system, but if we just are slightly less greedy than we might otherwise be, it doesn't matter that we can't change the RMS displacement. If we say, okay, there's going to be some frequencies where there's going to be thermal noise, a strategy we can adopt, and it is the strategy that we have adopted, to say, let's take away as much dissipation as we possibly can. Then, at almost every frequency, we have reduced the thermal noise spectrum at the expense of just completely ruining a narrow frequency band that was basically going to be ruined anyway, no matter what the dissipation level was. Let's just cram all of the RMS in a narrow resonance and get the benefit of low dissipation in the low thermal noise, on both sides of the resonance. So that's our strategy. Give up every place there's a resonance and make sure that the broadband noise is as low as we can possibly make it by reducing the dissipation to as low a level as we can. All right. Now, I've been using the concept of Q. I think people have talked about quality factors of off and on this whole week. Let me, before I show you these words, show the thing I like better, a few diagrams that describe what we mean by the quality factor Q. One way of finding Q is a dimensionless figure of merit that tells you how little dissipation you have in an oscillator. The less dissipation, the higher the quality factor, the higher the Q. So here's one way to measure the Q. One way to define it is to say, let's set a system in oscillation and watch the exponential decay of its amplitude. And the Q is pi times the resonant frequency times the decay time. If I'm looking at the response of my system in the frequency domain, I can define it as the ratio of the resonant frequency to the full width half max of the resonance. Or it also turns out to be the case that it's the ratio of the height of the peak in a frequency response to the low frequency shelf of the response. 3 different ways of measuring it. They're all the same. And they are measures. This is precisely a measure that says the higher the Q, the lower our dissipation level. Oops. Now, there's yet a 4th way that I didn't diagram that we can measure, that we can define this and measure this, and that's an inherently frequency domain one. Let's go back to my system where I have the system I care about and I can drive it and measure the response. If there were no dissipation, the displacement would be precisely in phase with the force below resonance or precisely out of phase above, but let's think about below. And a good measure of dissipation is the phase lag between that perfect in-phase character and the response we actually get. The more dissipation, the more phase there is. So if you measure that phase lag in radians, it turns out that that phase lag is just 1 over Q. So that's a 4th way to measure it. All right. Now, how big is Q, or how big can we make it? Well, that depends on if we are good craftspeople and we don't make any blunders in our design, then the Q factor of the crucial resonant structures in our system will be governed by the materials out of which they are made. So one thing you want to do is ask yourself, okay, if I made a spring out of steel, or out of tungsten, or out of glass, or out of rubber, or out of whatever, and ask what's the phase angle between force and displacement, and measure Q, build ourselves up a little bit of a handbook of materials. You'd be hard-pressed if you were trying at all to end up with a Q worse than 1,000. I'm saying hard-pressed if you were trying at all. I'm excluding making things out of rubber. Now, we sometimes make things out of rubber when we really want a low Q, but if we're building something that we want to have a nice resonance. Any kind of metal you pull off of the shelf and make a spring out of it, the Q is going to be around 1,000, speaking in round numbers. If you go to some care and select a good material, you might be able to make something with a Q of 1,000,000. That takes, you're restricting your choices there, but that can be done. And if you're really aggressive, you can find 1 or 2 materials where Q is 10 to the 8. So that's kind of the range of design freedom that we have. All right, now, how does this come into an interferometer? One nice way to think about this is to analyze the mechanical parts of our system one resonance at a time. Sometimes it's not a good idea, but for conceptual purposes, it really is. So let's focus first and foremost on one of the most important resonances in our system, the pendulum mode of the test mass hanging from its wire. So if we explicitly plug in a model for a resonant system, and so the pendulum mode can be a perfectly good example of that resonant system, I can calculate the admittance, calculate its real part, and write down an expression for the whole power spectrum of the thermal noise for that system. And here I have written it explicitly. So here is the K-Boltzmann T factor. Here's a pi left over from that 2 pi f squared. And the admittance has brought in some other frequency dependencies. You can see that there's a resonance in this denominator. There's a frequency for which this expression here vanishes. But the whole denominator doesn't vanish because there's finite dissipation. Here I'm characterizing it by 1 over q, this loss angle phi. And the remaining measure of the dissipation that shows up in the numerator is the loss angle as a function of f. And let me point out one other thing, that inside these square brackets is a classic resonance denominator, but there's also one other factor of frequency floating around here, which surprises a bunch of people. And in fact, it surprised me at first. But I also need to say something a bit more about this phi of f. So when we have an individual resonator, there's one and only one Q. If you measure it by the full width half max of that resonance, or by the peak height, or whatever. But if you realize that there is a dissipation that's being introduced at all frequencies, then you really ought to think about this phase angle, this phase lag measurement between the applied stretching force on a spring to the response. And then you see that this phase angle is in fact something that's defined at all frequencies. And in a moment, I will say more about that and say more about the 1 over f. But let's see. I actually want to skip that and maybe come back later. Do I want to do this now or come back later? I'm going to come back to those 3 things. So if it looks like I haven't come back to slides 22, 23, and 24, remind me. Okay, so let's talk about how we make the dissipation small. The first thing we want to do is do what I call good craftsmanship. Pump the air out from around the pendulum so the mirrors aren't swinging through something that gives dissipation. Make sure that all the mechanical connections are really nice, solid, welded things, no rubbing. Make sure that there aren't magnets moving near conductors to give eddy currents. Any of those things can make excess dissipation that will be a driving term for excess Brownian motion. And then we're in a situation where it is the material out of which, the material that flexes when my degree of freedom is displaced, that's where we get dissipation. So for example, in a pendulum wire, the wire under its tension is mainly straight, but it does bend up at the top, and once we have an extended mass, it also bends at the bottom. And so if we've engineered things right, it's the internal friction in the pendulum fiber that will dominate the dissipation budget for the pendulum mode. If instead we're worried about the Brownian motion that's associated with the fact that a mirror itself has vibrational modes of its own, then that tells us, okay, what is it that stretches if you were to excite an internal resonance of a mirror? Well, it's the bulk material out of which the mirror is made. So those are our crucial materials if we engineer things well. What's the dissipation in the pendulum fiber? What's the dissipation in the mirrors? All right, now I'll go back to this slide. Living in the 20th century, I've got some numbers for the initial LIGO suspensions. They had a Q of around 10 to the 6, which is maybe a bit of a surprise when you realize that the wires were made out of steel, and steel has a Q of 10 to the 3. However, there's a really cute thing that happens with pendulums, which is why we chose and continue to choose pendulum suspensions as the way of making our mirrors free, as opposed to putting them on some other kind of soft spring. And the answer is this. It's got a grand name. The jargon name in our business is dissipation dilution. But the idea is relatively simple, whether you like the name or not. So if you ask the question, what's the restoring force that brings a mirror back to the vertical after you displace it from vertical, it's not primarily that flexing wire, even though that flexing wire is the thing that is the spring you can see. What is it that's the main restoring force that brings a mirror back to vertical in a pendulum? It's gravity. Okay. And to a very, very, very good degree of correctness, there is no dissipation associated with that gravitational force. So actually, a pendulum has two springs attached to it in parallel. It's as if letting the vertical motion in this diagram stand in for the flexing. It's as if I had a strong spring and a weak spring attached to my mirror in my pendulum suspension. The strong spring is the gravitational spring, and it has no dissipation. The weak spring is the extra elastic restoring force that comes from the flexing of the wire. This has some small dissipative fraction measured by its phi, 10 to the minus 3. But if I ask what's the fraction that that small amount of dissipation has in the overall spring constant, it gets divided by the fact that there's a much larger ideal dissipationless spring, namely the gravitational thing. So even though I can have a steel fiber that has a loss angle of 10 to the minus 3, the combined spring of that weak spring and the strong spring could have and did have loss angles of 10 to the minus 6. And it's only what is seen by that measurement of dissipation, treating this as a black box, that governs the fluctuation dissipation theorem. So if I dilute this dissipation by mixing it with a very strong purely dissipationless spring, I do in fact get the thermal noise benefit from having made a much higher Q oscillator. So that's an explanation of why you always see pendulums as the final stage of our suspension systems. All right, now I want to say a little bit about what we do and what we don't understand about the physics of internal friction. And the physicist in me recoiled from saying physics of internal friction because we're going to get into the murkiness of material science, and depending on when you wake me up, I sometimes think that that's physics and sometimes I don't. That's maybe for discussion over tea, whether that's fair or not. But let me wade in here anyway. So the first thing I want to say is that the way we were taught to think about damped oscillators in our beginning physics class as a force proportional to velocity never happens in materials. There is never in quotes. We don't generally have materials that are well described by an internal viscosity, by something that gives a dissipation force proportional to velocity. Over maybe narrow frequency ranges, sometimes yes, I'll show you. But that is not a good model. And you know it's not a good model because all sorts of musical instruments exist, like a xylophone. Okay? And you have a piece of metal that's long and fat, and you hit it and it has a low frequency resonance. And then a piece of the same stuff that's really short, and you hit it and it has a high frequency resonance, and they both make beautiful musical tones. And if there was as much frequency dependence as velocity damping would give you, namely stronger frictional force proportional to the frequency, you couldn't make xylophones. They'd be dead at the top range. Okay, so you already know from the existence of music that that velocity damping is not a good model for friction in materials. The model that you see in the material science literature for internal dissipation looks more like this. Let me first walk through this and then say what physics is behind this. So the model looks like a main spring and then a little weak spring in series with a dashpot. What does that actually represent physically in a material? The idea is that, let's say I've got a bar of some stuff and I flex it a bit. Typically that stuff is not a perfect crystal. Typically it's got a whole host of different kinds of defects. It's got vacancies, it's got interstitials, it's got dislocations. Consider one kind of defect and ask, is the location of each of the examples of that kind of defect inside the material, might those things migrate under the application of a stress? And the answer is generally yes. So another way of interpreting that is for short time scales, those defects don't have time to migrate. In effect, they kind of provide a little bit of extra stiffness. But then, after you've flexed that material for a while, they start to find the happier places under that applied stress, and the material will give a little. And this is very generic. And if you have a population of precisely the same kind of defect over and over and over and over, then you can model it by saying there's a characteristic relaxation time that you can make out of this combination of a dashpot constant, effective dashpot constant, and the strength of that stiffness. And on time scales that are short compared to that relaxation time, that material is as stiff as the sum of this main spring constant and that little extra one. But on time scales that are long compared to this relaxation time, the stiffness is only associated with this main thing. And because there are many different kinds of defects, this is kind of a fun thing. In fact, this became a tool for exploring the microscopic dynamics of materials. Try to find situations where this phenomenon is happening. And you can find this phenomenon happening if you're careful. Here is what the frequency dependence of a real material modeled as a pure spring and then a spring dashpot unit looks like. So this is spring constant as a function of frequency, solid line for the real part, dashed line for the imaginary part, as a function of frequency, log scale. Now, if you look really carefully, you can see a slight step up in the real part of the spring constant at high frequencies. That's saying if you're applying a sinusoidal flexing to that material at high frequencies, it's stiffer than if you do it at low frequencies, because at low frequencies, those defects have had a chance to migrate and soften the material. More interesting for us is the frequency dependence of the imaginary part, which is going to be the thing that gives us our real part of our admittance. And if you work out the dynamics of a spring with precisely that model, what you see is a pretty broad peak in a pretty broad peak for the dissipation as a function of frequency that says over about a decade or 2 decades, you've got strong dissipation centered on the frequency that's the inverse of the characteristic relaxation time for that particular kind of relaxation, but that at frequencies far away from that relaxation frequency, you've got at low frequencies the equivalent of velocity damping, dissipation that grows with frequency, but at frequencies high, you've got 1 over f. So internal friction ought to look like this. And sometimes it does, but in fact, it usually doesn't. And I will come back to the one case that we often see. Where did I write it? Okay. I no longer remember what slide I wrote this on. I'm just going to say it. In real materials, you don't have anything like that pure statement of one kind of defect with precisely the same activation energy for hopping over a barrier to its new place. Even if you are dominated by one class of defects, there's always a spectrum of energy barriers. And the spectrum doesn't even have to be that broad to give you a very wide range of relaxation times. And once you have a broad range of relaxation times for a dissipation effect that is already pretty darn broad, what you end up normally seeing is that the imaginary part of the spring constant, which gives the real part of the admittance, becomes almost frequency independent. And so that's why I can say steel has a Q of 1,000. What I mean by that is whether I make a 1 hertz spring out of something out of steel or a 100 hertz or a kilohertz thing, it almost doesn't matter. The oscillator, if the dissipation is dominated by flexing in that steel spring, I'm going to see a Q of 1,000. And that's something that material scientists hated to admit. When I was first learning about this and I started calling up the experts, oh, no, that's excess dissipation. We're not interested in that. We're interested in these relaxations because that's a fun thing to study. But I said, oh, I don't care about what's fun to study for you. I want to understand what I actually see when I build stuff. Says, oh, no, don't embarrass me by bringing up the stuff we don't understand. So it's funny, it's hard to find this in the literature, although I did eventually find a paper from I think it was the first decade of the 20th century. So paper in Physical Review where a couple of guys said, okay, I'm going to measure Q as a function of frequency for a whole bunch of different materials, and boom, 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 boom. He said it's frequency independent, and here's the numbers. It was completely forgotten, except for the fact that we all kind of knew it because we all listen to music and we know musical instruments work. Now, there is one kind of relaxation that we often see in pendulums. There's a kind of dissipation mechanism that comes from this way. Every material you might make a pendulum wire out of has a finite coefficient of thermal expansion. Now, let's think about how that works in reverse. Flex a pendulum wire. That stretches one side of the wire and compresses the other. So running this physics backwards, it says that momentarily you set up a temperature gradient across that fiber. One side gets hot, the other side gets cold. If you don't immediately let it go back, heat has a chance to flow across and lets that fiber relax a bit, gets less stiff. So it is, in fact, it follows precisely the dynamics of that thing I diagrammed that I didn't utter the name of a Zener model. And it turns out for the kinds of materials that we tend to choose and for the thicknesses that we tend to choose, the characteristic frequency for that relaxation is often in the frequency range that we care about, between 10 hertz and a few kilohertz. So whenever you're designing a pendulum and worrying about, say, the thermal noise associated with violin modes, you have to check, okay, for the choice I made of material and diameter, the diameter comes in because the shorter the diameter, the quicker the heat flow across the wire. Did I end up building in some extra dissipation from this so-called thermo-elastic damping? Yes, Uni. A bell. Mm-hmm. 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 Mm-hmm.
That is already an example without making specific measurements, that all of them coexist for enough time, almost suggesting that the high frequencies actually the Q might be even larger.
Well, yeah, we'd have to actually listen carefully to check that. And do remember that there's a lot of acoustic damping on bells, otherwise we couldn't hear them. So my oral memory tends to hear maybe the high stuff dying away and a fundamental lasting longer, which would still be consistent with what I'm saying of frequency-independent damping. So I don't want to agree too precisely with what you're saying without thinking it through. But roughly speaking, what you say is correct. Yes.
In practice, to make the oscillators, does it happen that high frequencies of Q is actually a bit better for many methods?
Not typically. No, not typically. I mean, the existence of this thermoelastic effect means that you can get, you know, sort of any frequency dependence you want, depending on where that thermoelastic peak happens, if it shows up at all. But even so, the basic rule of thumb seems to be that whatever frequency dependencies you see are much weaker than a power of frequency, except when you encounter that thermoelastic effect. Okay. Frequency-independent damping is the norm. Here's my handbook of chemistry and physics. Rubber has 10 to a few tens, metals 1,000 to a few thousand. Here is the miracle. Sapphire or very pure and very defect-free silicon tend to have ultra-high Qs, and everyone says, oh, of course, right? They're good crystals. Not, of course, because crystals can support all sorts of defects. So, but sometimes they're what you think. But the amazing miracle is that fused silica has this remarkable Q if you treat it well. Okay? If you don't ruin it by damaging the surface, which we try very hard not to do, or by filling it up with impurities. So in other words, if you get ultra pure fused silica, not something that has a lot of dopants in it, or if you don't put multi-layered dielectric coatings on it, which unfortunately we have to do. So far, Yes, please save us from this, Rana. Okay, we were talking about this on our way in this morning. But with 20th century physics that's still applied in advanced LIGO, it turns out that fused silica is so good that that very thin coating that we put on the front of our test masses to make them good mirrors actually dominates the dissipation and therefore dominates our thermal noise budget. So to go to third generation detectors beyond the advanced generation, solving the coating problem is a really important thing. There is an important frequency range where we expect that the dissipation from the mirror modes will be important. And now I want to close, since I've run out of time already, with a graph that I should have put in my slides but didn't. So here is log of frequency, log of power spectrum of thermal noise displacement. And now I want to draw for you the thermal noise spectrum alone of what we expect in our interferometer. Here is our pendulum mode at 1 hertz. Here, starting 10-ish of kilohertz, is the fundamental internal vibrational mode of the mirrors, and then a spectrum of a whole lot more. Our gravity wave measurements are going to be made in this frequency range. Immediately above the pendulum resonance, we have 1 over f. Well, let me make this, I'm sorry. Let me do what I am more comfortable doing. Let me call this the amplitude spectral density. Okay, not the power spectrum. 1 over f to the 5 halves. 4 of those 5 halves are the 1 over f squared response of a pendulum, and that extra square root of f comes from the fact that our power spectrum expression had that resonance denominator, and it had a extra phi of f over f. Only for the case of velocity damping would we expect 1 over frequency squared, but when we're in the presence of frequency independent loss angle, we get an extra 1 over root f. Similarly here, we expect a shelf that looks something like 1 over root f. And when you look at what the advanced LIGO optical design could have done for us if we push things in this middle range of frequencies, we can make it so that the quantum noise, that is the combination of shot noise and radiation pressure that we really wanted to dominate our noise, bottoms out around on top of this expected level of thermal noise associated with the internal vibrations of the mirror. And this is higher than it ought to be for fused silica by quite a bit because of our highly dissipative mirror coatings. So thermal noise was just barely not a problem in initial LIGO, but it definitely strongly affects the design of advanced LIGO, and if we're going to go any farther, needs to be solved for future generations. Okay, sorry I ran over. Let me end here. Any questions before we hand it over to Ron?